Welcome to AI Paper Podcasts. Today, we're doing a deep dive into a really pivotal study from CMU that maps out, with incredible precision, the relationship between the big three stages of LLM development.
Yeah, this one is on the interplay of pre-training, mid-training, and RL on reasoning language models. The authors are Charlie Zhang, Graham Newbig, and Sheng Yu, a fantastic piece of work.
Absolutely. And our mission today is to finally get some clear answers on that big, messy debate about reinforcement learning. Does it really extend a model's ability to reason, or is it just polishing skills it already learned in pre-training?
And this paper gives us four, I think, very clear headlines. For a quick summary, the big picture is that RL isn't some magic bullet. It's an amplifier, and you have to aim it just right.
Okay, so what's the first key takeaway?
The first is that RL only produces, genuine capability gains, what they call extrapolative generalization, when you train it on data at the model's edge of competence.
It's edge of competence.
Exactly. Not too easy, not too hard. And when they calibrated it correctly, they saw gains of up to 42% on the really hard tasks.
Wow, okay. That's a massive finding right there. What's number two?
Number two is that for a model to generalize across different topics, what they call contextual generalization, it needs a latent seed from pre-training.
Seed.
Yeah, like a tiny foothold. It turns out just 1% exposure to the basic building blocks of a new topic is enough. But if you have zero exposure, RL completely fails to make the jump.
Got it. So you can't build from nothing. What's third?
Third, they show that mid-training is a super powerful lever, especially when you're working with a fixed compute budget. It's this bridge phase that really strengthens the model's reasoning priors before you even get to RL.
And the final point.
And finally, a big one. Process rewards work. Instead of just rewarding the final answer, they verified the intermediate steps of the reasoning.
To stop reward hacking.
Exactly. And it didn't just stop bad behavior, it consistently boosted generalization and fidelity, giving them a solid 4 to 5% improvement on the toughest problems.
Okay, let's unpack all of that, starting with the controlled framework they designed. Because honestly, understanding their method is why these results are so believable.
It really is. For years, the big problem in LLM analysis was causality, right? You'd fine-tune a model with RL, see it get better, but you could never be sure if it was learning something new or just, remembering some pattern from the billions of pages it saw on the internet.
You couldn't isolate the variables.
Exactly. The field was kind of stuck. So what this paper does is it strips all that noise away. They built a synthetic, fully controlled environment based on 3 key principles.
So what's the first principle?
First, they build controllable synthetic tasks. They use math word problems, but here's the brilliant part. They represented the reasoning as a dependency graph, a DAG.
Which gives them a perfect objective measure of complexity.
A perfect measure. They call it op of G, which is just the count of arithmetic operations. So instead of a vague idea like this problem is hard, they could say this problem's an op equals 20. It's like counting chips on a circuit board.
It's so clean. And the second principle?
Observable processes. Because the reasoning follows that parsable graph structure, they could check every single step of the model's work. There was nowhere for it to hide faulty logic.
Which is crucial for their evaluation later on.
Absolutely. And the third and maybe most important principle for this study was systematic distribution manipulation. They created totally separate, completely clean data sets for pre-training, mid-training, and the final RL phase.
So no contamination.
Zero. If a model was pre-trained on problems from, say, op equals 2 to 10, they knew with 100% certainty it had never, ever seen a problem with a complexity of 15 or 20. Any success on those harder problems had to be real generalization.
And this framework let them test 2 really specific types of generalization. The first was extrapolative generalization.
Which is all about depth. Can the model solve problems that are structurally more complex, longer chains of operations than anything it was trained on?
And the second type?
That was contextual generalization, which is about breadth. Can you take a reasoning skill the model learned in one context, like, say, a zoo animals theme, and have it apply that exact same logic to a totally new teacher school theme it's never encountered?
And we have to mention their evaluation protocol, because it was strict. For a problem to count as a pass, it wasn't enough to get the right final answer.
No, not at all. They used what they call process-verified evaluation. Both the final answer and every single intermediate step in the reasoning graph had to be perfect, 100% correct.
So no credit for lucky guesses.
None. This makes their pass at K scores a true measure of reasoning fidelity. It's not just about what the model knows, but how it knows it.
Okay, this brings us right to their second section, the calibration challenge. They wanted to figure out the exact point where RL stops just refining a skill and starts genuinely extending a model's capabilities.
Right. So they start with a base model that's only been pre-trained on what they call in-distribution or ID tasks. These are problems with a complexity of 2 to 10 operations, stuff the model is already pretty good at.
And then they apply RL using data from 4 different difficulty levels.
Yeah, this difficulty ladder is the core of the experiment. You've got the ID tasks the model already knows. Then you have the out-of-distribution or ODE tasks.
And they split the ODE tasks into 2 groups.
They did. There's ODE Edge, which is complexity 11 to 14, and ODE Hard, which is 15 to 20.
And that ODE age category is the really interesting one.
It's the sweet spot. These problems are harder than anything in the pre-training data, but the base model isn't totally lost. It still has a small, non-zero chance of solving them if you let it try enough times a non-zero pass at 128. They call this the solvability gap.
A gap that RL can potentially bridge.
Potentially. And then you have ODE Hard, where the base model is just guessing. Its accuracy is near zero.
So what happened when they applied RL at these different levels?
The results, which you can see in their figure 3, were just so clear. For the easy ID tasks, RL only helped the pass at 1 score a little bit. The model got a bit more confident.
But the pass at 128 score, the measure of its total capability.
Didn't budge. No extension of capability at all. So if the task is too easy, RL is just sharpening a pencil. It's not teaching anything new.
But for the harder O tasks, that's where the magic happened.
That's where it happened. They found that RL only delivered consistent major gains in pass at 128, that true capability extension, when it was trained on the OD Edge data.
The stuff that was just beyond its reach.
Exactly. When the data was too hard, the reward signal was too sparse for the model to learn anything useful. But when it was calibrated to that edge of competence, that's when they saw that incredible plus 42% gain.
So this takeaway 1 in action. Real gains require targeting RL data right at the model's current limit. It's like weightlifting, right? You have to lift a weight that's challenging, but not impossible.
That is the perfect analogy, and it gives engineers really direct, practical guidance. When you're building an RL dataset, don't just find hard problems. Find the problems where your model currently fails on its first try, but can sometimes succeed with more attempts. That's your solvability gap. That's where you'll get the most bang for your compute buck.
Okay, so that covers depth. Let's talk about breadth. Section 3 gets into this idea of pre-training as a necessary seed for contextual transfer. What does a model actually need to know beforehand to transfer a skill to a new topic?
This is a fundamental question, right? Is the model just memorizing and replicating patterns, or is it truly generalizing a reasoning structure? Can a model that mastered a complex problem about lions and tigers apply that same logic to a problem about teachers and students if it knows nothing about schools?
So how did they test that?
They kept the logical structure, the dig, exactly the same, but swapped the context. And they varied how much of the new context's atomic primitives, the simplest op equals 2 building blocks the model saw during pre-training.
From 0% exposure all the way up to 10%.
And the results were, again, just striking. If the model had 0 or even just 0.1% exposure to the basic vocabulary and concepts of the new context,
RL failed.
it completely failed. The transfer just didn't happen. The model couldn't generalize the skill.
It needs a foothold.
It needs a foothold. But here's the breakthrough. They found that introducing just a 1% exposure to those atomic building blocks in pre-training was enough. That was the seed it needed.
Only 1%.
Just 1%. With that tiny seed, RL could robustly generalize the complex reasoning structure all the way up to op equals 20 into that new, sparsely seen context.
So this proves RL is more of a compositor than a memorizer.
Exactly. It takes the basic building blocks it learned in pre-training and combines them in novel ways to solve harder problems. Their analysis even showed that on the complex tasks, the model wasn't just copying structures from the old context, it was generating genuinely new reasoning structures in the new context.
Which is takeaway 2. RL needs these latent seeds to work its magic across new domains. You can't compose from a void.
And the practical advice here is huge. It suggests you should shift your pre-training strategy. Instead of aiming for massive, uniform coverage of everything, you should prioritize broad but maybe shallow coverage of the atomic rules and vocabulary across many domains.
Get the 1% seeds in place everywhere.
Right. And then you can rely on more efficient methods like RL to build the deep compositional complexity on top of that foundation. It's a much more compute-efficient way to build a generalist model.
Let's move on to the next piece of the puzzle then. Mid-training. The paper makes a strong case for this intermediate phase being a really critical but maybe underappreciated step.
I think it's hugely underappreciated. This section is all about optimizing your training process under a fixed compute budget, which, is a reality for almost everyone.
So mid-training is that phase after the broad pre-training, but before the very targeted RL fine-tuning, like continued pre-training or instruction tuning.
Exactly. It bridges the gap between those two very different data distributions. They wanted to see how allocating your compute budget between mid-training and RL affects the final performance.
And to do that, they had to normalize the cost of RL, right?
Yeah, they came up with a token equivalent cost for RL, which let them compare different budget splits fairly. They tested everything from a full mid-training run with no RL to a full RL run, and then a few mixes in between.
And what was the optimal strategy?
Well, it turns out it depends on your goal. It's task dependent, which is a really important insight.
Okay, so let's say my goal is reliability on tasks that are just a little harder than what the model was trained on, those ode-age tasks.
For that, the best strategies were either full mid-training or a mix with just a little bit of RL, like a 20% allocation. Mid-training is fantastic at stabilizing the model's priors, making its output more consistent and reliable on those more common but still challenging tasks.
But what if my goal is different? What if I want to push the absolute limits and solve the hardest problems possible, the ode-hard tasks?
Then the strategy flips completely. To maximize performance on those really difficult, never-before-seen problems, you need to reallocate your budget heavily towards RL. The 80% RL budget did substantially better there.
So it's a trade-off.
It's a classic trade-off. Mid-training buys you reliability and consistency in the middle ground. Heavy RL buys you exploration and the potential for breakthroughs on the hardest problems.
Which is takeaway 3. Mid-training is a huge lever for generalization, but you have to be smart about how you use it. Prioritize mid-training for reliability, prioritize RL for maximum exploration.
And it really provides a solid theoretical foundation for why modern training pipelines work the way they do. A strong mid-training phase makes the model RL ready. You're installing the stable priors first, and then you're scaling exploration with RL.
Okay, that brings us to the final key finding, which tackles what is, for me, one of the biggest headaches in this whole field: reward hacking.
Oh, it's a huge problem. This is where the model learns to trick you. It gives you the correct final answer, but it gets there using completely broken or nonsensical reasoning.
The internal logic is wrong.
It's totally wrong. And in compositional reasoning, that's a disaster because it means the model hasn't actually learned the skill, it's just learned a shortcut. So to fight this, the researchers introduced process verification right into the reward function.
So instead of just getting a reward for the final output, R out, they added a reward for the process, RPV.
Exactly. RPV is a dense reward. It gives the model feedback at every single step of the reasoning chain. They tested different mixes, but they also tested the strictest version possible.
Which was what?
You only get the reward for the final answer if the entire reasoning process was verified as 100% correct. No credit for lucky guesses, period.
And the results? Did it work?
Undeniably. You can see it in Figure 7. Integrating process verification boosted performance across the board. That strict, fully verified version consistently increased the pass at 1 accuracy by a solid 4 to 5% on the hardest OD tasks.
And they figured out why it works so well, too.
Yeah, the error analysis shows that process verification actively steers the model away from making specific kinds of structural errors, like connecting to unrelated facts or completely missing a step in the logic. It forces the model to learn reasoning that is structurally sound.
And that's our final takeaway. Process-aware rewards are essential for aligning the model's behavior with what we actually want, which is valid reasoning, not just a valid final answer.
It's crucial. The practical guidance here is crystal clear. If your task allows for any kind of step-by-step verification, you should absolutely invest the effort to build that into your reward signal. It will make your training more stable and ensure you're actually reinforcing the skill you care about, not some clever shortcut.
What's so amazing about this entire study is just how it uses this clean, controlled environment to demystify so much of LLM training. It really feels like it settles the debate. Reasoning isn't about one magic phase. It's about a delicate, synergistic interplay between all the stages.
And it proves that RL is an incredibly powerful amplifier, but only if you give it a solid foundation to work with and aim it at the right target.
So if you're out there designing an LLM training pipeline today, this paper literally hands you a 4-step roadmap. It's so actionable.
It really is. Step 1, seed the base knowledge. Get that minimal 1% coverage of atomic primitives during pre-training.
Step 2, bridge the distributional gap. Use mid-training to stabilize the model's reasoning priors.
Step 3, target the model's limitations precisely. Calibrate your RL data right at that edge of competence.
And finally, step 4, ensure fidelity. Use process rewards to stop reward hacking and enforce valid reasoning.
It just gives us the empirical evidence we've needed to move forward. We now know for a fact that RL can achieve true compositional generalization. It's not magic, it's just good architecture and careful calibration.
Okay, so let's end with a final provocative thought. This paper has established that RL can successfully combine existing learned primitives into solutions for complex problems it's never seen before. The next great frontier, then, might not be just making models bigger. It might be defining the absolute minimal set of core primitives a model needs during pre-training to unlock robust generalization across any domain. How few Lego bricks do we actually need to be able to build anything? That feels like the next big question.